in person and joining us online. I'm sure you are from C2 Smart, USDOT University Transportation Center. And today we are pleased to be joined by Dr. Carmelo D'Agostino. He's a senior lecturer of engineering at Lund University in Sweden, and is consolidated and internationally recognized experience in modeling the relationship between safety and road characteristics and the development and application of these models for assessing the safety of roads and the safety effects of design and management decisions. Carmelo's research interest is going towards how to evaluate safety in new mobility scenarios. On this topic, Carmelo has been recently awarded with a European Research Council grant with a project proposal related to the development of new scientific method to evaluate the effects of infrastructure on the interaction of connected and autonomous vehicles and conventional road users. So with that, I'm going to hand things over to Carmelo, who's going to take us through the presentation. Thank you very much.
Thank you.
Sorry, just one note also is that for folks online, if you want to ask questions, use the Q&A button at the bottom of your screen, and then we will take those at the end.
Okay, thank you for the nice presentation. I will introduce myself a little bit, and Lund University, for the one who doesn't know Lund University, where it is. Probably no one of you, except Kant, maybe. We'll see. But we are a big university. Lund is one of the biggest university in North European university. We have 8 faculties and more than 30 world-leading research field in our university. Very, very successful university. We are constantly in the top rank of the university in the world. We have more than 7,000 employees and more than 40,000 students. This is the idea how big is Lund University environment. And also, they call Lund the city of ideas. And just for let you know something, Lund University invented the Bluetooth that you use in your phone, or other things, a lot of things. Skype was invented at Lund University, and other things there. That's still different. Plus, of course, we have a strong collaboration with Volvo and with the Swedish car industry. So Polestar, Volvo, Saab, and Scania, of course. Well, I did my PhD. I did my master at the University of Catania and my PhD at Ryerson University in Toronto. And where I work mainly on accident modeling and road safety assessment. I had my supervisor, probably you know him, it's Baban Perso, and I worked a lot with, during my PhD with Ezra Auer, that helped me a lot to develop part of my PhD. So I'm really, really happy. When I moved then I decided to move back to Europe, and I landed at Lund University in Sweden, where I'm mainly working on non-accident indicators. And I recently established, and we got a grant for the virtual reality traffic safety hub. This is also what I will talk to you today about what is this hub and what is content. And of course, I'm the leader of the traffic safety group at Lund University, and we are 4 seniors and 2 PhD students. But now, with the European Research Council project plus other projects I will tell you today, our group is becoming 3 times bigger in the next 1.5 years. So it's a group is starting to grow up. So I'm quite interested. So this is just to give you an idea on what we will have in the lab, or at least what's the idea of this lab. So we want to be as much as multidisciplinary as possible. So we have, we want students and postdoc to have a good mathematical background and software engineering background, and of course transport engineering. We want behavioral science because we want to develop this model, these behavioral models of automated vehicles interacting with conventional road users and relate this to infrastructure. And of course, we have a lab technician. And a lot of external help. Part of the money, super safe, it's the European Research Council project I will talk to you about later. I don't know if you know what the ERC is, but I will explain this. And we also have other help, or we have money specifically for international cooperation. What we want is create this group. We want to know what other people are doing, and we want to let know other people what we are doing during this. Why simulation? As you see from the title of this seminar, why we want to develop simulation. And to know this, you should at least have a very short background of the conventional approaches on traffic safety, seen from the infrastructure side. I'm a civil engineer, we work on infrastructure. We don't work on vehicles. Of course, we collaborate a lot with vehicle industry, but we are not direct involved in research for vehicle. I think you know this, all of you know this. Who doesn't know this, it's just, it was developed in Sweden actually, in my same university, in the room close to mine, where I'm living now. Of course, Crystal Luden is retired now, but he's the one who invented this pyramids. So only a small part of the critical events on the road, so accidents, are only a small part of the events that happens when users interact each other. But there are also a lot of other events. So severe accidents are a very small part, thanks God, it's just very few. And then you have a lot of other events happening on the road. The idea is, okay, this is clearly not working, is something like this. What we are studying is events that are not an accident, but are close to be an accident. This is non-accident, what we call surrogate measure of safety or non-accident indicators. You know, I mean, you know some measure of it. You probably have heard about time to collision, post-encroachment time, or this is just 2 indicators of surrogate safety measures, but there are several of those. This is in Sweden, actually. We are ashamed about this because Sweden is one of the safest countries in the world in traffic safety. But there is some intersection. This is actually very close to my place in Malmo. There are several intersections that need really some attention. What happens? So when we talk about surrogate safety measures, we look at those events. So events that are not an accident, but can be developed into an accident if some correction is not taken by one of the 2 users. This is also surrogate safety measures. It's not just a vehicle with a car. It can be 2 bicycles interacting each other. It's still a potential accident. So the conventional method is clearly based on surrogate safety measures. Is clearly consider events that have the potential to become an accident. And then you study this and model this. How? Well, the same way you model or you try to predict accidents. So the highway safety manual. So this is conventional approach to traffic safety right now. Of course, this is very good because it allows transferability and everyone knows about the highway safety manual. We will not spend one single. So why we want to develop a new method? Why we're spending all this money for understanding how safety works or how safety can improve? Well, of course, when you introduce new animal, completely new animal in the traffic environment, and you want to understand how safe they are, if infrastructure are good enough or safe enough to allow a safe interaction between the new vehicles, the new element, and what is already existing in the road. But policy and legislation not ready for this, since we are not seeing automated vehicles on the road. But I can tell you because we work, as I told you, we work a lot with car industry, they're pushing hard to have automated vehicles on the road. They want to sell those vehicles, but of course, we don't know. And why policy and legislation are not ready? Because we don't know what are the implications for road infrastructure. We don't know if our roads are safe enough. The accident-based approach, but also the surrogate safety measure approach are inadequate enough, or at least we don't know if they're or not. And this is why, mainly because we have no data on automated vehicles in open traffic. So you can see, we cannot have automated vehicles, and at the same time, we cannot have data to analyze their safety. But with simulation, we can create this new behavioral model. We can try to understand how human, conventional drivers interact with automated vehicles and how infrastructure affects this interaction. We can develop a new accident prediction method, maybe based on surrogate safety measure. We can adjust the risk concept. So we can try to, because the problem here, this sentence a bit vague, but consider that if you consider an accident as the product of exposure and risk, the measure of exposure and the measure of the risk can be completely different, because the interactions between road users is maybe even more, you want that there's higher interactions. So maybe the exposure anymore, the ratio between exposure and risk can be completely different in this case. And of course, we need a multidisciplinary simulation platform, because we really need to understand how people interact, how humans interact with these new vehicles, new automated vehicles. Well, how we do it? I will briefly tell you about these three projects up running at Lund University. I'm the coordinator of these three. FFI is, Endel is one of this. As the interaction, we develop a new prototype of handlebar for bike with vibration and haptic feedback. And we are trying to understand if the interaction with automated trucks and electric trucks in urban area to improve this interaction. The main problem of urban truck or electric trucks is that you cannot hear them. And when interact with bike, bikers often has headphones. You cannot. It's very dangerous interaction. Autoliv is one of the biggest company in the world. It's Swedish. It's one of the biggest company in the world for developing a solution, safety solution for vehicles. And now they are starting to develop solution for the electric e-scooter and bikes. They have like the 50% share of the market for safety in vehicles in the world. So it's a huge company. When you think to Sweden, you may think to Volvo or to IKEA or to Ericsson, Sony Ericsson. But I can tell you that Autoliv is probably the biggest company in Sweden. We have another project. FFI is the Swedish Innovation Council, International Innovation Council. We have another project with Volvo. It's called Advice. Again, we are studying the interaction of automated trucks, but seen from the truck. They are interested to alert the driver of the truck that there is a bike, or if the bikers is aware of the presence of the truck. This is not easy because there should be a double interaction. So you should communicate to the bike that there is a truck, and you should find a way to understand if the rider is aware of the presence of the truck and send information back to the truck. In some particular interaction, and you will see now how we do. And of course, we have the ERC. Few words on the ERC. You're not in America, so probably you're not aware. It is the European Research Council. Is a huge European funding for researcher. It's literally free money for developing a very risky, scientifically risky idea on research idea. So the concept I risk I gain, it's very high at the ERC project. So just few words about Handle and Advice project. We built our own simulator, bike simulator, by scratch. We didn't buy it. We decided to develop in-house because we decided virtual reality hub. We didn't want a fancy simulator. We want a simulator that can work on what we are doing. So this is the haptic handlebar that we had in the simulator. And this is a very old bike. We choose it because of the history of the bike. We wanted something different, not fancy, but someone, and we choose actually used bike. We bought it on purpose. Just to let you an idea of how the simulator works. It's a very simple concept. This is the test part. We have a VR and with a 3D view. We built all the environment, of course, in Unity, and this is the concept basically. So you see an example of how the simulator works. And we build the virtual environment in using Unity. We had to choose about Unity and Unreal, the two software. We probably work on these two. The two like game engine that works better. We choose Unity because it was simple to use, and this is how the environment look like. Of course, this is a real environment. We put 3 drones up that can cover at the same time. We can cover the entire area. We make a survey of the bicycle and vehicles at that time. We use the bicycle tracking for validating our results, and we use the traffic, the real traffic, for the test. So in a way we can simulate, but I'll show you in a second. We reproduce the handlebar in the virtual reality because using a VR, you really need to have the active feedback vibration you can reproduce. And when we started was so strong with people on the same floor, the other part of the corridor started to complain about the vibration, but we managed. But for the visual, using VR, you need something to interact. This is not ideal, but for us was really convenient to use a VR environment instead of having screens around. It makes our more immersion. It's easier to see. So we have different scenarios. I will not bother you with this, but I will show you the results of what we had. So we have basically, we try to simulate as much as we can the interaction with the truck and also the interaction with the infrastructure. We had several all participants in the 3 scenarios. We use quantitative and qualitative data in collaboration with the companies. We develop only the quantitative analysis. They work mainly on the qualitative part. So some questionnaire after the test. And we had 24 participants in total in these experiments for these 2 projects. And 2 aborted due to sickness. That was the main problem in the project. And we are writing in our paper to try to, because probably we understand how to reduce sickness in the simulator, but this is still not there. And I want to show you what it came out. So this is the environment built in the simulator, and you will see soon this is all the people that run the test. this is with all the trajectories. You see some people going around. Yeah, we had some defiance, of course. And the vehicles are not agents. They don't interact with the other road users. This is the next step we will have in the ERC project. Right now, it's only vehicles passing. It's the only the participant that interact with the infrastructure. So this was another scenario. This was with the HMI. So you can see that when the HMI is in action, became red on the truck and the bike. And of course, some bikers bike much faster than others. So, but we are happy about this. We are actually happy about this. So basically, the point here is that simulation was the only possible way to study this and arrive to this conclusion. So we strongly think that the simulation environment is still need a lot of work because it's not ready yet for arriving to conclusion, has to be strongly validated. But at the same time is extremely powerful to the researcher right now to study new environment and future environment. And exactly what we are trying to do at right now at Lund University. This is very interesting, actually, is the truck turning right with the HMI system. So we realized that when in the worst condition, so the truck turning right interacting with the bike, the use of HMI, so HMI is this new handlebar system, it works quite well because this bus was completely, the truck was completely silent. So it's a real very good solution for understanding if the HMI is working or not. Of course, we do some tests on the real world in a controlled environment. We don't want to kill any students. And so we will try to validate these results soon on our project. And you can actually see that was with HMI. So you see basically the truck, the people stopped waiting for the truck turning. This is without what happened without HMI. So the same participants run without and with HMI. And you can see that the behavior is completely different here. There was people almost killed by the truck. They don't care, they didn't reduce the speed, they just continue for their own way. So in this case, we can see the simulation is able to reproduce reality in some way. Of course, this is the first step again on this field, but we will keep, we are still keep working on this. This is just another example. We use simulation in this case for, we simulate a portal on the ground, and we try to understand if you have if the HMI advise you that there is a portal in front of you, what happened to the driver, to the rider. I can tell you that didn't happen anything. They didn't care because unfortunately infrastructure is more on virtual reality is much easier to simulate the interaction with other world users, but much more difficult to simulate interaction with infrastructure, at least for bikes. Here seems to be very, very slow. I don't know. Of course, it's a numeric simulation, so we have all the information about the position, speed, acceleration on each of the participant in the experiments. Well, yes, this is what we look at, not really interesting. So speed, lateral distance, pedaling, braking, steering. And we have the large variation among participants, and mainly due to we also run a test, ask them to reply to a questionnaire to understand if this variation, we can measure the same variation in their capacity or ability to ride a bike. So how many days advanced they ride a bike, and so their attitude on biking. And there is some patterns. The results will be probably published soon. And unfortunately, this eliminate this variation is not possible, and it's not even visible for us. Reward this variation. How we validate them? As I told you, we basically had 3 drones running at the same moment. And this is a real environment. And we had a ghost bike coming, is a real bike. And we let the participant to the test running starting at the same, when the same bike start the environment, then we try to understand if they bike together with the bike. So the blue bike is the bike, blue truck is the bike, the real bike, and the other the participant. They are not, there's a big difference, of course, but the difference are not statistically significant. So we use this as validation for our test. Of course, there are different ways to evaluate things on virtual reality, and we should have much more real bikes running on the same track. But that was quite interesting to notice that the trajectories were not that far from the original bike, the real bike. This is just an example. This is the same thing but seen from from a closer perspective. So this is the ghost bike, and this is all the participants of the test running. Of course, the participant did one by one. Then we put all of them together. We synchronize the time from starting, and then to put all of them together in this track. Let me explain a bit more about SuperSafe project. So my years. I want to be clear on this. The project is not started yet. We'll start in January 1st. We seek for collaboration on this specific project. We will build an advisory panel on the project, and we will keep you updated if you want, of course, on what the project is, how the project is developing. I want to show you or tell you a bit more what it is. As I told you before, it's European Research Council grant 2021, even if it will start January 1st, 2023. The idea is, it's all behind the project is quite simple. We want to observe real scenarios in the real world. Build a virtual environment. We have traffic there, we have vehicles. We want to build a virtual environment starting from the real world environment, and had automated vehicles and run experiments on the driving simulator. So the first step is build driving simulator experiments, and for calibrating behavioral models of conventional road users interacting with automated vehicles. How now we do the behavioral automated vehicles? We will, I don't know if you are aware, probably you're aware about SAFER, the research center in Gothenburg. No, it's a basic research center on traffic safety in all the North European countries. But it's open to all the countries in the world, actually. And it's an excellent center, actually, on traffic safety, and leading, of course, by car industry, with a lot of money there, and Chalmers University. And they are partners. And the project is an individual project, so that's, but they agree to get help through SAFER for calibrate the behavioral models of the automated vehicle interacting with infrastructure. Volvo has this data, and Scania has this data, the real world, and we'll probably get data from there for calibrating this behavior. And the idea is have these behavioral models in the specific situation and implementing these behavioral models in a micro-simulation environment. Why? Because in a micro-simulation environment, you have not human in the loop, of course, but still you can randomize parameters. So if you know how human interact with how the infrastructure affects these interactions between automated vehicles and conventional users, then you can randomize parameters and try to study the environment of all the study in a micro simulation. So get more data, basically. And as for the project itself, we are interested to extreme events. So we want to develop this new method for understand how infrastructure affects these interactions. So just to be clear, a crash modification factor, an accident modification factors, as you're probably more familiar with, using non-accident based indicator and extreme value T is the basic idea of the project, of the method. So with the simulation, we cover just a small part of this curve. Is a curve that fits an extreme value theory or general operator. And we are interested in this value. So if this is events or is an indicator, this is the distribution of the safety indicators, time to collision, just to be clear, we're probably not going to use time to collision, because we know it's not working and probably not even post-encroachment time, but something more simple. If this is the distribution, this is what we observe in the simulation, in our environment, in our micro simulation environment. We are interested in what happened here. We are interested in the extreme events, to the events that are more likely to turn into an accident. And we will probably run some real-world validation out of it. We plan the project in the Super Safe project for the validation of this part. Of course, you cannot validate the method of estimating the number of accidents because you don't have solutions about this, but you can observe how humans interact with automated vehicles in a controlled environment, safe and controlled environment. We probably do that several test bed. I mean, there are in US too, but the US too, but we have several in Europe. And there is one in Sweden that is a European premise. It's called Asta Zero. Probably we will run the test at Asta Zero. Okay, this is not working, but I will show you later, maybe using another software. I just wanted to show you what I mean about this. We already observed some scenarios in the real world with real conflicts, and we create a simulation of it. So we are able at least to have the digital twin between the real world and what happens in a simulation environment. Well, what the high gain? You remember I talked about high risk, high gain for the European project, for this kind of European project. Well, it's the first thing is we want to understand, we want to fully explain the interactions, those interactions between road users, considering the behavioral adaptations. Because when you have automated vehicles, the first period will run. It's not a good indicator of what happened in the long run. So you really want to understand what is the final result. What will happen in 20 years, in the next 20 years? How people will adapt to automated vehicles and which will be the real safety in those specific conditions. And of course, the other things is that we want to conduct safety analysis based on non-accident indicators. It's a very high gain on the project because we want to evaluate, we want to have a proactive approach to infrastructure when we have automated vehicles. So we want to know exactly before you introduce automated vehicles, how what's the expected number of accidents in the specific condition, and if we can improve it, of course. What's groundbreaking? Why the European Commission decided to give money, a lot of money for this project? This is, of course, this is very interesting because we don't need to wait to have automated vehicles on the road to understand our safety. But we will do before. And of course, we try to validate this data with observations on a controlled environment. So we adjust the concept for risk from reactive to proactive in this specific case. We want to introduce a new accident prediction method, and that maybe can also be used for real-time implementation of the vehicles. If the method works, you can actually understand based on the exposure you have in the specific moment, what the risk you are, or what's the expectation of observing the accident in the specific condition. And of course, the idea is to create a simulation platform that testing future mobility scenario. As, of course, a proactive thinking to the future, but that's exactly what we want. We want to create something that's very flexible, which we can, very dynamic, we can study and develop new solutions for infrastructure and vehicles and test it immediately on a simulation environment with these new behavioral models and this new, eventually, micro simulation if it's needed. So we're not going to use a commercial software for micro simulation. We are building our own. Simple, not fancy, but we want to really know the nitty-gritty details of those interactions and be very flexible in the implementation of the behavioral models we want to study. So this is basically what SuperSafe project is. And in Sweden, we have Vision Zero. We have also this the concept of safe system parliaments that is not Swedish, just being implemented in Sweden now. So no one new things can be implemented in the road if you're not testing, if it's safe before. So from this perspective, Europe has a big different approach than North America, which is not necessarily better, but it's just different. And Sweden in particular is very devoted to safety. So we really have, we have to be very careful when we develop solutions for safety. So basically this was all from my side, but I just wanted you interact with me and let's talk about this a bit if you want, and I'm very happy to discuss.
So I have a quick question.
Yes.
So every company implementing autonomous vehicles, they have their own algorithms.
You know.
So the claim is that you will have some kind of a setup to test them after they deployed it, or you want to do this for like a generic AV? So what is the, I mean, like a main approach? Because
Yeah, this is one of the main problems we are facing now, because several, even like in Sweden, we have Scania and Volvo, two companies, they don't collaborate each other. They're two different worlds. And their automated vehicles interact in a very different way with infrastructure, in different conditions. If they have the same sensors, but of course the algorithm works in completely different way. And we will try to get the higher variation possible on this. So we will try to implement both. This is why we didn't want to have a driving simulator we built our own driving simulator by scratch. We are building our own driving simulator by scratch. We want to be sure we are the maximum flexibility possible to test at least 2 or 3 different solutions, so 2 or 3 different car makers, OEMs, and try to understand if they really makes a difference the specific condition. Of course, in the ERC project, we will limit a lot the possibility of because we are focusing on some specific use cases. So we will test those specific use cases, and we cannot validate the method for all the possible use cases, all the possible interactions. So we will try to focus on those specific cases. So it's since it's quite narrow, it will be easy to do that because you can let the people drive in the same scenario 3 different times with 2 different way of the automated vehicles interact with infrastructure, and then try to understand if this difference affects the behavioral models of the drivers. But this is, of course, one of the main problems we're facing in the project. Yep.
All right, so I have 4 separate questions.
Yeah.
The first one is, what would it take to make the trucks and the simulator agents? So you have right now just the bikers are the agents and the trucks are a fixed route. What would it take to develop some sort of behavioral response so that way you have that interaction between the biker and the driver? We
actually have it. We actually developed it already. I told you when we ran the simulation, the truck is not an agent.
Right.
It's just a complete separate entity, so it doesn't interact with the bikes. We developed this project was I don't know if you remember, I mentioned 2 projects. One was Endo with Autoliv, the other was Advice with Volvo. The one with Volvo, the bus is an agent. We had the simulator, a multi-functional simulator. So we had the truck simulator and the bike simulator working in the same environment. So we studied those interactions. So it was an agent because it was a human driver. We cannot show the results because Volvo is a very strict. They will probably commercialize the system. So we are not able to, at least for the next 6 months, to show anything about this. But yes, this was done. The results are really, really interesting. Really, really interesting.
So the next question is, you talk about different types of vibrations you would send as haptic messages to handlebars.
Yeah.
Right now, we're looking at interactions between the bikes and trucks. You also consider interactions between the bikes and maybe infrastructure like potholes. Is there a concern that there might be too many types of interactions such that that information becomes overloading and stops being distinguishable to the biker?
Yeah, this is very funny because we tested the system also in the real world. And I can tell you, the first thing is it's not really centered on your question, but it's partly. The main problem was try to find the right frequency first to make a difference between the infrastructure, the normal riding, because on a simulator, wherever is the active feedback, you don't get, because the simulator is standstill. So you don't need really to study this. But on a real world, it was completely different. We really need to find the right frequency. Then we try to change it, to try to give a different information to the rider. Because with the truck was easy, the truck is coming on your left or on your right, depends on when you're on the bottom. And then you have only the right side or the left side, like vibrating or blinking in your bike. And that was extremely powerful tool. We realized that was very useful. The bottle, we just gave the information that there is something in the road. The risk that you are giving too many informations and then the rider stops to looking at them is very high. But it is part of the behavioral adaptation of the system, and we cannot test it in simulation. Not at least on the bike. But it's of course a very interesting thing.
Next was, so you said that you're building your own agent-based simulator in-house.
Yes.
Is there a plan to open source this? Do you plan to have the agent-based simulator stay entirely internal?
Yes, the idea is to give completely open source. Above all, if we get funding from European Commission for doing this, we have to. And we are completely open to collaboration because we really need to we want to create a network in the platform. So we are really happy if someone wants to use our simulator to tell us, and we will give all the information about the codes we are using now for the experiment we are running. We cannot give you the results of the experiments, not at all, because we are working specifically, these two were developed together with these companies, so we're not allowed to do it. But we can absolutely share all the rest of the information and the simulator itself. So with our approach.
Just let me ask, so you want your own microscopic simulator?
Yes.
I mean, there's, like, of course, you know, there's something like SMoS, which is also open source. So,
Yes.
I mean, I understand that it's maybe more detailed than what you want, but I mean, writing your own simulator is a major endeavor. That there's always going to be a question that people will say, is it really accurate? Is it really doing the job?
Yeah, I think SUMO is an option. We are evaluating now what to do. What we are not using is a commercial
Of
software.
course,
That out of any.
that's out of question.
Yes, out of question. SUMO is an option, absolutely. We already developed a part of the simulator, of the microscopic simulator for surrogate safety measure for study specific interaction, vehicle turning right and vehicle crossing.
Yeah.
And we developed in-house a part of this new software, and is working quite well. But on a larger scale, probably going to use SUMO.
Yeah, because I mean, some of these models that you mentioned can be incorporated into SUMO.
Yes.
I mean, because I did that in prehistoric times for my master's. I wrote my own simulator, but I'm not a software engineer, so it was always kind of very iffy. If somebody else used it, if I used it, it was fine. But if I gave it to someone else,
Was not.
it was.
Yeah.
So and then we heard here, Professor Tarek Syed. He's also like developing his own microscope. I mean, my concern is that this is a bigger thing, and everybody doing their own thing. It becomes very difficult to share these tools and also to make sure that they're and up to a certain software engineering standard.
Yeah, I agree.
Yeah.
And probably SUMO will be the best option. And
I mean, it's not the best, easiest thing to use, but once you get a handle on it, I think it's not.
Yeah, no, I really think it's the
They're
best.
not here, but we have several students who are
Working on
using
SUMO.
SUMO for this kind of work. Jenny is here actually.
Okay, we are hiring. We are hiring 2 postdoc and 2 PhD students. So
Yeah, one of them should be done next semester. Hopefully.
I'll move to Europe.
So my point is, it's difficult to learn, but once you learn it, I think it gives, and also, I mean, because there's such a large community using SUMO.
Yeah, that's absolutely an option. That's absolutely an option. Yes.
That's great. For the bike, when will you decide when to send the notification? For example, you have a truck approaching, is it because it's speeding? Is it there's a sensor on the bike itself? Are they communicating with each other?
Is the distance from the bike and the truck in the specific case? We are assuming a straight distance of straight speed of 30 km/h in the urban areas, because it's wind and it's 30 km/h. And we are the lateral distance between the two makes the difference in the activation of the HMI system.
And how do you get that?
You get that from the position in that specific case. The position, yeah, the VR, you know exactly is a numerical simulation. So you know exactly what's the distance between the person is riding the bike, the tester is riding the bike, and the truck is passing.
So Susanna is in your own bike sensors for real bikes. She can show you after your.
Yes.
It actually measures the distance, the lateral distance in real life, so I have it the real.
So she puts the sensor on the bike and she measures it, the lateral distance in real world.
Okay, that's very interesting. Very interesting. Yeah, we didn't measure that distance. We had the simulation. So right now, our idea was just to test the interaction of the rider with the HMI, but we didn't focus on developing any sensor to measure the distance.
And you mentioned the safer lab. I actually, my research, I get lots of inspiration from Mark Mendoza. He's one
Yeah.
of them.
Of course,
Yeah.
we work on that.
Yeah.
I actually had the same similar question because I was curious about to know about how you actually do the risk measure and whether you were doing this proximity. Now I know it's only proximity based, but have you considered doing the trajectory prediction?
Yes, of course. This was the main things. This is one we want to develop. We want to have this real-time or forecast of safety. So alert the driver when there is a risk of to proximity, when the proximity is not there yet. Yes, this is absolutely what we want to do. And we were going to use the same idea we had before. We were going to use for this exactly the same thing we had before. We're going to use this. We try to understand if there is any in this, because then you need to understand what's the probability, then this trajectory would be, you get too close, and we were going to use this. This is univariate, the specific case. When you predict accident, we use a bivariate, because we try to understand the probability of observing an accident, and the probability that this accident is severe enough. So we use proximity and energy, the two things. So this is monovariate. We use a bivariate system now we're focusing on another system, another idea. We have another idea on the mathematical side. So we're not even doing a bivariate extreme value theory. We're going to use a copula approach. This is completely different, but the concept is the same. We want to predict severe accident. We don't want to predict slight injuries or even a PDO. Yeah.
So you mentioned that this research is high risk, potentially high reward. You've described the potentially high reward. What is the risk?
You mean the risk of the research itself, or the risk of the concept of risk in the?
Well, you said that it was funding for high risk.
Yeah, the high risk is that the European Commission is spending 1.5 million euro to don't arrive to any meaningful conclusion, because the research is very, looking at future, and you may not get any very useful results on the scientific level. But if you get results, they're very relevant for the community. And this is the high risk, high gain concept in the European Research Council.
So, first, we have a question online. So it's, do you think data from virtual environment represent an accurate measure of the real world?
Well, this is a very good question. We don't know. We really hope so. We try to validate the real world, the simulation, the real world data. So we start from real world data, and then we try to build as much as we can. We try to base our validation on real world observation. Of course, you cannot observe automated vehicles because you don't have automated vehicles. So for this, we are just trying to validate the behavioral models we are developing in the project, in the ERC in the specific case. So we try to reproduce the same things in a controlled environment, real world controlled environment, and we try to understand if the human react in the same way. But we cannot validate the methodology because we don't have observation. I mean, you have SHRP2 database on accident on automated vehicles, and we may try to have access to this data and try to validate our model, our method, if we can, of course, but I'm not 100% sure. Of course, we can do it. But yeah, it's a very good question, and it's actually, we don't know if it works.
Another question.
Okay, I can ask,
Yeah.
so, she was there, I think she might have had to leave, so, it's okay, go ahead.
Okay.
Okay, sorry, I think she did.
Yeah.
So,
Yeah.
Professor Zimmerman's from our, Wagner School, so she said, is uncertainty of both the bike and truck riders taken into account due to factors such as distraction, experience in driving, riding, etc.
Yes, this was what we did. We tried to test or to know the attitude, the attitude to the rider, so to the participant to take a risk in their driving. There is some questionnaires. We had some questionnaires before starting the ride, which we asked them questions to try to understand what's their ability to ride a bike. So how often they ride a bike, so you can understand how good they are in the riding. And also there were some questions to try to understand their attitude to take a risk in when they ride. And this, of course, we hope to correlate this variation, the standard deviation, the variation in these answers, with the variation in the quantitative data we have in speed, lateral position, and so on. But this is one of the most difficult things to do. And if you have any tip for this, it's really, really welcome, because we don't really, it's a completely new field, mobile with the bike, and we are really eager to collaborate, or if you have any idea on tips on this, we'll be very open to answer. The ERC will not be with bike. I don't know yet if I want to insert a scenario which I will have a bike interacting with an automated vehicles, but maybe. But in this specific case, probably we have just vehicle to vehicle interaction.